Log on, tune in, find out. Another good idea from Cambridge.
Final speaker of the session is Ben Haaland.
Thank you. And thank you to the organizers for inviting me and putting together a great conference. It's been a lot of fun. So my topic is accurate emulators for large-scale computer experiments. So certainly more than some, 27 or 8 runs, and this is joint work with my advisor and my academic sibling. All right. So a little outline. I won't spend much time talking about computer experiments because that would be pretty silly. I probably won't spend a ton of time talking about emulators, although I have a little bit, maybe a different perspective than totally standard. And go through an error decomposition into numeric and nominal error, and then introduce this multi-step interpolator and develop some error bounds for it. So please interrupt if I say something that doesn't make any sense. Just ask. Okay, computer experiments, as everyone knows, complex mathematical models to study real systems. There's a lot of situations where it's not feasible to do a real experiment. Could be impossible, expensive, unethical, inconvenient. And often you can produce sort of input-output pairs with the help of the computer. And I'm going to focus on deterministic computer experiments, so no stochasticity. That the runs are expensive enough that you can't just gather as many as you want. You can't sort of use the computer simulator to do sort of exploration or optimization. So we've seen lots of examples, climatology, engineering, there's others, ecology, systems biology. This is kind of an old, actually, example from IBM. They do consulting work on helping companies design data centers, and they have big heat equations. There's heat sources and fans and stuff, and expensive software. They can't sort of these runs of these heat equations, I don't know, they might take a day or half a day or some of them even a couple of days, and they can't sort of find the optimal place to put all the fans and stuff using this. They need to build an emulator. So everyone's probably on board with that, would be my suspicion. So oftentimes we want to sort of explore this unknown surface, and too expensive to use the computer model to do that. So solution is to evaluate the computer model at some well-distributed sites, maybe space-filling designs with low-dimensional projection properties that are nice, and then we can build an emulator or interpolator, which we could use as stand-in for the real experiment. And we can carry out our exploration on the interpolator. So nothing new so far. Yeah. So Gaussian process interpolators. So oftentimes people use a Gaussian process to build an emulator. Maybe I will say something that's a little bit new. So if instead you look at it as a reproducing kernel Hilbert space interpolator, in some kind of sense you're making a weaker assumption. Say you say, okay, I think my function's going to have continuous second derivatives. So then, in a way, if you get the covariance parameters wrong, so there might be some parameters in this phi, it's still going to have the property that you designated for it. There's kind of an inherent norm hiding in there somewhere that maybe isn't weighting smoothness in quite the optimal way, but you're not sort of violating your assumptions in the same way as if you say that there's a true covariance parameter. Well, so anyway, typical building block for these type of interpolators, some kind of covariance function, symmetric, positive, definite, and I don't remember, I guess, the notation everyone else uses. I don't think they use the script P. That's my Gaussian process interpolator. It has a nice simple form. It's a linear combination of these basis function evaluations subject to this interpolation constraint, and we solve a linear system and can get that. And then associated with this choice of kernel, there's a Hilbert space of functions. Say, maybe a typical one is it has continuous derivatives of all orders if you use like a Gaussian kernel. I usually use continuous second derivatives, just, I don't know why. It seems like a little weaker. So there's some space of functions that these p's, script p's will live in. And then there's some kind of a norm that's going to sort of measure how smooth the function is and how big it is. So this is the thing that if you specify those parameters incorrectly within your phi, you might not have quite the optimal norm in there, but you'll still have continuous second derivatives. So it'll be in the right function space, but maybe not sort of the optimal interpolator. So these reproducing kernel Hilbert space interpolators, they're kind of, they have the smallest native space norm of any interpolator in that space. So once we decide the space and some particular norm of interest, this is the best that we can do. So maybe a little different perspective, but it is a Gaussian process if you just look at it in a different way. So this is in a lot of ways similar to Pritom's sort of issues that he was talking about earlier. So I'll motivate it. So a lot of the systems people are interested in, they have quite complex behavior, certainly in particular regions. Maybe there's not much going on, and then there's some strange drop off, maybe in the data center example, as you turn the corners around some rack or something, there might be some complex behavior. So understanding these regions where there's the complex behavior, you're going to have to get data points that are close together. Or maybe if you've collected some data using optimization routine, you'll get some data real close together. And as Pritom was saying earlier, you get numerical problems. As the data points get closer and closer together, the two corresponding rows of your interpolation matrix become closer to one another. And then as they get identical, it becomes singular, and everything kind of flies off the handle at that point. So just the whole problem, sort of in a general sense, becomes ill-conditioned as the data sites get close together. And there's a lot of techniques, nugget effects, compactly supported kernels, correlation decompositions, and the technique that I explore is this multi-step interpolation, and it's not really meant to replace any of these other methods. It's my PR portion, just as a complement to these other methods. So now let's just introduce a little notation and decompose our error into two parts. So we have the thing that we pretend we have when we're working with the computer, that's x. But then we have the thing that we really have, which is x tilde, which is x subject to numerical error. And I'm going to distinguish the two. So we have idealized or nominal quantities, x's, and then we have x tildes, which are the ones that the computer kind of spits out and we actually have to work with. And, we can apply the triangle inequality, and we can get this separation of the error. So we've got our function, and we have this thing that we're using to predict our function, p tilde. And so for any norm, the difference between those two is less than the nominal error plus the numeric error. And so I'll sort of go after those two pieces separately. So a lot of what one sees, is stuff relating to this nominal error. There's some results out there. But in a lot of problems, this is sort of the thing in the driver's seat, the numeric error. So I'll develop some bounds on that. And this is true for any norm. We could be looking at absolute values, L2 norms, native space norms, whatever. Well, let me skip back here. So often there's a trade-off between the two. Clearly we can get very low numerical error if we just have spikes at the data points, but then when we look at the quality of that interpolation, it's not going to be anything like what we want. And then we can get our nominal error low by having a wide, smooth kernel, but then it's going to be difficult to invert this matrix. So there's typically a pretty strong trade-off between the two. So one thing that you can show is you always, I'll just say it in a loose way, you always reduce your error by adding more data. And so this is less than or equal, so it's not maybe strict. You don't maybe strictly reduce it. And this is in the native space norm, so this is in a bit of a funny space. But you can always, essentially, you can always make things more accurate in nominal error by adding more data. Even if you have a data point, you put one right here beside it, it's going to reduce the nominal error. Okay. On the other hand, if you imagine you have a nicely spread out data, no numerical problems, you can imagine introducing a bunch of data to make your numerical problems much more severe. So an example, you can do mathematical examples, but they kind of hide the meaning somewhat. So imagine you're going to build an interpolator for this function. It has a nice picture. It's not too hard to interpolate. And you're going to use these red and black points. Well, you're not going to use these red and black points. So these ones look pretty reasonable. They don't have nice projection properties, but they're nicely spread out. And you're not going to use these ones either. You're going to use these ones. And there are distinct points. They're just sort of hiding under the red points. So you had the black points that were fairly nicely spread out, and then you add to them these red points that are not quite on top, but I think they're 10 to the minus 10 away. And so by adding this data, you haven't, intuitively, you haven't contributed any real information. You've just made it sort of numerically intractable. So, well, if you pump this into some kind of optimization routine to find your proper kernel width, it's going to say your kernel doesn't have any width. And your error is going to be something like the L2 norm. You're just going to have spikes at your data sites. So by adding those sites, you sort of you make your numeric error much larger. So you can see that when you add data, you always increase your nominal accuracy, but you could do just about anything to your numeric accuracy. So some applied math people, Floater and Isk, back 15 years ago, I guess, proposed this multi-step technique, which I'm going to modify a little bit, but basically use what they proposed. And the basic idea is to thin, or their basic idea was to thin the data out and fit a nice smooth model, and then make residuals on, well, if you were just doing 2 stages, make residuals on the rest of your data, interpolate those residuals using something that's not as smooth, then add the two together, and you have an interpolator. And it's kind of like Roshan's, but a little different, and certainly geared at different data sets. So yeah, interpolate the first subset using sort of a wide, smooth kernel, form residuals, and then interpolate the residuals using something less smooth and more narrow. And you could do this a lot of times. It doesn't have to be 2 stages. It could be, I think I use cap J. It's my number of stages. So a little toy example, some kind of sines and cosines with different amplitudes added together. And it's a little bit small, but there's 100 data points here. And you can imagine taking every other data point. So you take 50 data points and you form an interpolator, and this is also a picture which is a little lacking. There's an interpolator in there. And then you can imagine forming residuals. So in this top plot, every other residual is 0 because you interpolated that point, or 0 plus numerical noise, which is small for this example. And then you can imagine interpolating this thing with rougher kernel. I think I don't actually use a rougher one in this case. This is just to see what the technique is. And then you add the two together, and this is on a little different scale than the initial plot, but this is the original function and the interpolator both plotted. You can see little jaggedness here and there. It's the interpolator. This is just has, it's a continuous interpolator, so it doesn't have any derivatives. It's just like connect the dots interpolator. So if you want to prove theorems about the numeric and nominal accuracy, you need some formulas. So these are the formulas I start with. So we have our jth level interpolator. It looks a lot like that simple form that we saw earlier, but it interpolates the errors here. So this is the difference between the function and all the previous interpolators. And we have our interpolation matrix. Nj is the size of the jth subset. So I didn't mention maybe that you need nested data sets. And two things I don't address but are actually quite important. One, what size should these data sets be? And then two, what kind of nice space filling properties should they have? I don't have a good answer to the what size they should be, but the space filling is quite important. Suppose you choose that initial data set that's got a bunch of points really close to one another. Well, you don't really gain anything then. You want it to be well spread. So all of these data sets need to be well spread out. We add up all of these different stage interpolators, and then we have our multi-step interpolator, maybe is what we've decided, I guess, to call it. So we give complete bound on the numeric error. There's no order of anything. It's sort of computable terms all through it. Computable in the sense that you can compute anything with a computer. You can't compute pi, but in the, you can approximate it to 16 decimal points with the computer. They're pretty weak assumptions, although they don't look very appetizing on first glance. So we start out with Gullib and Van Loan, the matrix computation book. You invert a matrix. That's kind of the primary thing that's going on, is the matrix has to get inverted. So we take a lemma or two in there and sort of doctor them for our own purposes. They just have the numeric error appearing once in here. For us, we're going to need to have two sort of errors, because we're going to add to the. So we have the idealized linear system and the numerical approximation to the linear system here. And each time we go through a stage of this numeric interpolator, we're going to add some more error to the right-hand side. This b is going to get a little extra error, so we're going to put another term in there. So this is kind of the lemma that we use, and this is, well, it's more or less from Gullib and Van Loan. It's a few results, kind of doctored, but and then you can get the numeric error for a single stage interpolator. So this is just Gaussian process interpolator. Single stage, that means just the standard thing that everyone here has probably done 100 times. So the assumptions look a little unwieldy. This one is just bounding the error of our computation of our interpolation matrix, pretty standard. Maybe this is 10 to the minus 15 or a little smaller than that. It's kind of a typical type assumption. Same for the function evaluations. They're the truth, the relative error is some 10 to the minus 15-ish quantity. One sort of thing, we have the condition number, pre-Tom defined earlier. And there's this R, which says how much are we going to bound that away from the point where everything crumbles. So as it gets to like 1 over machine precision, it just spits out strictly garbage. But you can think, oh, do I want it to get to halfway there, or do I want it to get 90% of the way there, or how to what degree am I going to restrain the condition number? That's this R. And then we have our kernel evaluations. They have some error they're subject to. So this says that for a single stage, our numeric error is related to machine precision, how much we're going to restrain this condition number. This thing here is sort of like a Monte Carlo approximation to the L2 norm. It's just the inner product of the function evaluations with themselves, and then this root n is in there so that it approaches the L2 norm if they're normally or uniformly distributed. And then this thing is sort of the piece that we can typically control. So we can, by making our kernel wider or narrower, we can control this minimum eigenvalue and this condition number. And then, so this isn't maybe quite how you want to see it initially. You probably want to see it in terms of like how far apart the points are. And so you can twist it into that. Well, okay, so that's not what I'm doing next. Actually, next is for the multi-scale numeric accuracy. So this looks pretty nasty. So there it is. The assumptions, there's kind of one new assumption, and it has something to do with if your residual process has more error than your initial process, which is not typically going to happen, but if you're doing mathematics, you have to sort of think, well, could I construct something that would make this happen? And you can, but you have to pay a bit of a price, but it's... So a couple of things here. You don't want to do a lot of stages because this number is bigger than 2, and it's growing pretty fast. And you're summing a lot of things up, so you want just a few stages. So I know there were some people who worked on this in the past and suggested doing 1 stage for each data point. Well, that's going to make this explode. It has sort of the same type of business as the single stage. It's got the computer accuracy, approximation to the L2 norm. These are sort of ratios of approximations to L2 norms. They're close to 1, hopefully, if you've got nice space-filling designs. And this is that thing that you can control by changing the widths of your kernels. So as I was starting to say, you probably want to see this in terms of how far away points are. And you can push that through, write it in terms of the minimum distance between any 2 points. You introduce this Fourier transform of your kernel, and you get basically that it's like a less than a quadratic function in this. So notice the numerator goes to 0, and the denominator, this thing, it turns out, also goes to 0, but it goes to 0 really fast. And the smoother the kernel is, the smoother the kernel is, the faster this denominator goes to 0. So couple of points, close together points lead to more numeric error, and smoother kernels lead to more numeric error. So like just connecting the dots, doesn't have near the numeric problems as using, say, a Gaussian kernel. Okay, well, it's time to be hasty. So you can also get a bound on the nominal error, and so previously I'd just been subscripting the kernels with a J, so that just means you can choose any kernel you like at any stage. Here I'm going to tie the kernels together a little bit more, and I'm going to have this rescaling. So I'm going to have some basic kernel phi, and then I'm going to rescale the inputs to sort of stretch it out in different directions and make it wider. And I'm going to use this fill distance, so the largest data-free ball, the radius of that. This is sort of a standard result that the difference between your real function and your predictor is less than some sort of stuff related to the fill distance to a power. And then if your function's really rough and really big, that's going to hurt you. And then your rescaling is going to be involved like this. So you can imagine, so when I was working on this, I thought, well, okay, this is where I want to start from. So I can peel off one term at a time using this relationship, but then I've got an f minus a bunch of these things over here. So I need a kind of a similar bound for native space norms. And you can get that, it turns out that it looks like this. So you can bound the native space norms in terms of convolutions. So each time you get one of these, you have to convolve the kernel with itself on the right-hand side. And then, there's a little bit of head scratching about, this theta, maybe I didn't want that theta, and how does that relate if I rescale it? And I'm going to skip that. That's actually a grotesque part of the development. It's fun to do the math, but it's not, it's kind of beside the point. I've only got 6 minutes, so there's some rescaling business. So in the end, what you get is that the nominal error is related to, or is less than some constant, and this constant relates to how smooth your basic kernel is and how many stages you do. And then so it's got the native space norm of the function and some kind of basic reference kernel. And you've got these rescalings, and maybe the big thing to notice is you've got these fill distances, and they're raised to a really big power. And so this isn't really in the driver's seat. It's really the numeric error. And if you think about, I said if the kernel has k derivatives, we have a k here. Well, you can imagine with the Gaussian, you've got 10,000 whatever. You can put in whatever number you want. So it's really these are sort of unattainable, these nominal sort of rates. They're sort of there's a lot of action going on in this C. It's kind of overwhelming everything. So. But it turns out that this all works pretty well. So a couple of examples. If we try interpolating Frankie's function using I like nets better than Latin hypercubes, but that's just my way as well. So I use a net to gather data from Frankie's function, and I think 625 points. And so single stage with me doing the best I can. This is my mean square prediction error. MLEGP, just as a reference, it doesn't do nearly as good as even just doing the best you can yourself. And then as you increase the number of stages, you get some improvements, but they taper off pretty quickly. So you don't want too many stages. It's 2 or 3 or 4. It's a good number. So how about a more difficult problem? So Schweffel's function, 5-dimensional. This is a 2-dimensional projection of this function. You can see there's a lot going on. It's a pretty tough to interpolate. Even I gather 400,000 points from this function, and it's still tough. And so previously I'd use cross-validation to choose my my kernel parameters. Here I just use a fixed. I choose my kernel parameters so that my interpolation matrix doesn't have too many non-zeros. I think I let it have 7 million or something non-zeros, and I say you're done. You're not getting any more kernel than that. And so we can also improve on this going by increasing the number of stages. MLEGP, of course, says no, you can't do that. So I'm gonna skip. Confidence intervals are available, but not as nice to come up with as a typical Gaussian process. The stages kind of introduce these dependent Gaussian processes. So there's some details in our paper. So we can use this technique to improve the accuracy of large emulators. And just some sort of guidelines. Numeric accuracy requires well-separated data points. Nominal accuracy requires small data-free regions, so big holes in your data are bad. And you can get confidence envelopes under Gaussian process assumptions.
Questions for Ben? Excuse me.
So you mentioned this as a complement or alternative to other existing methods that avoid numerical instability.
Yeah.
Could you give some guidance about when you would use this versus the other ones, especially with an eye to the other issue that comes about when you have a huge number of data points, which is huge computation times?
Well, I would probably use this because I know all about it. The nugget is easy to complement things with, so I would probably explore that as well. I'm not sure as far as head to head. Despite sort of what you see, this is actually pretty easy to implement. Just fit residuals and that kind of thing. I suspect if I had a problem that was sort of beyond what this could handle, I'd have to do some research, I guess.
I have a question about implementation. So you said that the designs have to be tested, so the selection of points rather from your suite of runs have to be tested. So suppose I've got 100,000 points, and the first stage I decide to take 1,000, just pretend I do, right? So you get this long range correlation. So now there's 100,000 minus 1,000, 99,000 points. Now, when you talk about residuals at that point, so you got to compute the residuals, do you include the original 1,000 back in, and so the residuals are all zero at the 1,000 points? Is that what happens?
That is, that's what happens.
Okay, wasn't sure. But,
And there's some, for selecting those points, suppose you have collected the data already, which is typically maybe the case. There's some thinning algorithms and stuff that are implementable and with sort of large data sets. The Floater and ISK paper, they go through an algorithm for thinning out your data. So getting sort of these relatively space-filling nested designs from an existing design.
When you're doing more like approximation theory with wavelets or splines, then you put some function space conditions like Bezos space conditions.
Yeah.
So it seems to me it's quite a critical term in these are wonderful bounds. I mean, but the critical term is the smoothness of the function. You kind of slightly you said you had a norm on what you call the native space, surely that norm has to measure smoothness. Can you tell us what it is? I mean, is it something to do with bounded third derivatives?
Those are typical. So like what Sobolev spaces and Beppo-Levy spaces are. So I think if you like a Matern kernel, if you choose that. So I think then it has a nice form. It's some kind of a linear, like a convex combination of absolute values of derivatives and the function values up to some, how many orders you say you have continuous stuff. You can compute it if you have a representation of the function in terms of the kernel. So like for your interpolator, you can compute its norm. It's some kind of inner product with the interpolation matrix in the middle, or the inverse of it. But for a general function, it's kind of an abstract quantity. But that is a key point. If say your function actually is infinitely smooth, then you'd be kind of shooting yourself in the foot by saying, "Oh, I've only got continuous second derivatives."
All right, very good. Well, I think it's time for lunch, and we'll see you all back here.
One announcement.